Hello, and welcome to our definition of the Fourier transform and an example calculation. The Fourier transform of a function f from the real line into the complex plane at a point k in the reals is 1 over square root of 2 pi times the integral from minus infinity to infinity of f of x times e to the minus ikx, also written f hat of k. The first thing we should ask is when in general is f hat of k defined? And the lazy answer is to say f hat of k is defined whenever the improper integral above converges. But can we get something more uniform, some condition on a function f that guarantees that f hat of k is defined for all real numbers k? If we take a look at the integrand here, we can calculate its modulus to be modulus of f of x times e to the minus ikx, is just modulus of f of x for k in the reals, and that's because the modulus of e to the minus ikx is 1 when k and x are real. So if we take f in L1 of r, then the comparison test will ensure that the improper integral above converges. So f is in L1 of r means that the modulus of f is integrable from minus infinity to infinity. Then the equality here between modulus f of x e to the minus ikx and modulus f of x ensures that the improper integral above converges from the comparison test. Be careful with this factor of 1 over square root of 2 pi. We are building this into our definition for the Fourier transform in this course, and so it will carry through and affect a variety of equalities and identities that we later develop. Different people, different books, different papers will put the 2 pi or the square root of 2 pi in different places in the Fourier transform, just like we saw with the 2p in Fourier series. Whenever you're reading a new book or a new paper, take a moment to identify the conventions associated with the Fourier transform there, and also for its Fourier series. Also, we are going to use the same hat notation as in Fourier series. The mathfrak big F on little f there is unique to Fourier transforms, but we will often represent things with hats, and that's what we use for complex Fourier coefficients of Fourier series. Context will always make it clear whether we're talking about the transform or the series, but pay attention. Let's do an example. Fix a number a greater than 0 and define big E sub a of x to be the piecewise function e to the ax for x less than 0 and 0 for x greater than or equal to 0. And we want to calculate big EA hat of k. I claim that big EA is in L1 of r for any positive a, and you will get to check that in the exercises. So if you believe my claim, you will know that the Fourier transform is always defined, so we can just go ahead and calculate. We use the piecewise definition. We start out with the Fourier transform. Big EA hat of k is 1 over root 2 pi, integral from minus infinity to infinity, big EA of x e to the minus ikx. And immediately we're going to kill off all of the integral over the positive reals. This becomes 1 over root 2 pi, integral minus infinity to 0 of little e to the ax times little e to the minus ikx. So that is just using the piecewise definition of big EA. And this becomes 1 over root 2 pi, integral minus infinity to 0, e to the little e to the a minus ik x. And here we've just combined e to the ax and e to the minus ikx into one exponential. So now we need to evaluate this improper integral from minus infinity to 0. And we can do this because a is a positive number and k is real. So if a is positive and k is real, what does this mean? A minus ik is not 0 for all k. Because otherwise, what would happen? A equals ik. So then when k is 0, a would be 0, and that can't happen. And when k is non-zero, a would be purely imaginary. But a is positive, so it's real. What does this mean? The antiderivative of e to the a minus ikx is 1 over a minus ik times e to the a minus ikx. So good old antiderivative of exponential raised to multiple of x. This tells us then that the limit as b goes to minus infinity of the integral from b to 0 of e to the a minus ikx that limit being what we want to calculate for the improper integral, is the limit as b goes to minus infinity of e to the a minus ikx over a minus ik. Evaluate that at x equals 0, subtract from that, evaluating it at x equals b. So we want to calculate the limit as b goes to minus infinity of 1 over a minus ik minus e to the a minus ikb over a minus ik. So what's going on in that second term? We will use the squeeze theorem to show that this second term vanishes as b goes to minus infinity. So take the modulus of the second term's numerator. It's modulus e to the a minus ikb. Do the multiplication in the exponent and split up the power. That's modulus e to the ab times e to the minus ikb. That's e to the ab, because modulus of e to the minus ikb is 1 when k and b are real, while e to the ab is always positive for a and b real. And this, I claim, goes to 0 as b goes to minus infinity, because a is greater than 0. So a is positive, b is negative. The exponent here is negative. You make b a big negative number, that e to the ab becomes very small. And here, to emphasize again, it hinges critically on taking a to be positive. So, big EA hat of k, our Fourier transform, is 1 over root 2 pi, integral minus infinity to 0 of e to the a minus ikx. That is 1 over root 2 pi, limit as b goes to minus infinity, integral b to 0 of e to the a minus ikx. And that is 1 over root 2 pi, a minus ik. Sorry, the ik got cut off here. However, I claim that big EA is not in L1. So this is interesting. I have the Fourier transform of a function in L1. I get a function back for all k, and yet this function doesn't land back in the vector space L1 of all absolutely integrable functions from minus infinity to infinity. Why not? I claim that the integral from minus infinity to infinity of dk over modulus a minus ik diverges. For the Fourier transform to be in L1, this integral would have to converge. Well, actually, of course, there's a 1 over square root of 2 pi in there, but the integral will converge if and only if the multiple by 1 over square root of 2 pi converges. So just think about this integral for a moment. We want to show this integral diverges. Here is a sketch of how that goes. We calculate 1 over the modulus of a minus ik is 1 over square root a squared plus k squared. Since a and k are both real numbers, this is just the definition of modulus of a complex number. But 1 over root a squared plus k squared, because you have that square root in there, it cancels out the k squared. This is roughly 1 over modulus of k for k large, or maybe some constant times that. And calculus tells us pretty quickly that the integral from 1 to infinity of dk over k diverges, sort of a p-test for integrals. So this integral in star diverges. But the comparison test would suggest to us that if big EA hat were in L1, then this integral in star would converge. And so we would get a contradiction if we had big EA hat back in L1. And you will work through this a little more precisely in the exercises with some further guidance from me and make this hand-wavy stuff rigorous. So what's the moral? We like our functions to be in L1 for the Fourier transform to be defined, but we need some stronger hypotheses if we want to guarantee that the Fourier transform ends up back in L1. And this will require no small amount of carefully stated, somewhat technical hypotheses on theorems to come this week and next week. The mapping properties of the Fourier transform as an operator on functions are delicate and strange, and we will get to have fun exploring them together.